Hello and welcome back to astronomy. So in our previous segment we were talking about Johannes Kepler and how he was able to come up with a formula that explained the orbits of planets around a star. And I said that Johannes Kepler really did not know why that this happened. Well, after Johannes Kepler came Sir Isaac Newton. And so if there is a Mount Rushmore of famous scientists, he would certainly be on it. So he was very brilliant, and so he lived during the 1600s and came up with his laws of motion, which we've already talked about. So the first law, the second law, and the third law of motion. Then he also came up with gravity. So he came up with a formula that explained gravity. So if you recall, that was the one that said big G m1 m2 divided by r squared was equal to the force of gravity between two objects m1 and m2. And then he also invented calculus. So what he did was he knew that the force of gravity, he knew what that was. He also knew what energy was. And so by using calculus on his formula for the force of gravity, he figured out the potential energy of gravity. And so here's the formula that he came up with. Notice it involves the big G thing because the formula for the force of gravity also has big G in it. You notice it also has m1 and m2, so it depends on the masses of the two objects. So like for example, Earth would be like mass number 1. And then let's say that this pen is mass number 2. And then r would be the distance from this pen to the center of the Earth. Okay, and so it would take a certain amount of energy to raise this thing because this has a certain mass. Now, let's try it with a bowling ball. It takes a lot more energy to lift that bowling ball because it has more mass. So you see the formula depends on the mass of the thing that it's in orbit around. It also depends on the mass of the other object, and then it also depends on the distance between them. So you'll notice that this one has a green box around it. So I'm not so concerned that you'd be able to put actual numbers into that formula, but could you do something like this? What does the gravitational potential energy of a rocket depend on? So going back to this formula, it would depend on the mass of the object that it's trying to escape from or go around. It would depend on the mass of the rocket, and it would depend on the distance that the rocket is from the planet. So that's basically all that I would want you to know about that particular formula. But one thing that's really, really important is if you look at the formula, do you notice it's got the minus sign on it? And that minus sign basically originates from the formula for the force of gravity, which also had a minus sign on it. But this is important because it says that gravitational potential energy is always a negative number. Now, let's compare that to kinetic energy. Okay, do you remember what kinetic energy was? So kinetic energy, or E sub k, was equal to 1/2 mv squared. It depended on the speed of the object. So the faster the object goes, the more kinetic energy it's got, and it also depends on the mass of the object that's moving. Do you notice that this is always a positive number, even if you're moving backwards? So if you're moving backwards, it's true you'd have a negative velocity, but what happens when you square a negative number? You end up with a positive number. So I want you to notice that kinetic energy is always, always, always a positive number, and that potential energy is always, always, always a negative number. And normally a rocket ship has both. So a rocket ship is going to have a certain amount of potential energy because it's going to be located a certain distance away from a planet that it's going around. And because it's moving, it's got kinetic energy. So what would happen if we add those two numbers together to find the total energy that the rocket ship is going to have? Okay, so what I want you to do is go to this PBS simulation, satellite motion. Okay, so find that on the internet because it's going to make this a lot easier to explain. And you'll notice that you can change the speed of the object that's in orbit around a planet, and you can also change the distance from the planet, and then you can hit the go button and then see what the object does. So first, I'd like for you to try it with 0 velocity and see what happens. Do you notice it crashes? All right, now try it with a little bit more speed and you'll notice it moves a little bit more, but it still might crash into the planet, or it might crash into it could be a rocket ship around a planet, it could be a planet around a star, okay? But notice if you get the speed just right, it will go into orbit around the object. Now you also notice it's telling you what's the kinetic energy, so that's the blue one. Do you notice that the blue bar is above and the red bars are below? So you notice the red bars, the first red bar is the potential energy, and then the second red bar is the total energy. So when you add the kinetic plus the potential, then you get the total energy of the thing. So notice that if the total energy is less than 0, that it goes around and around in a closed orbit, just like Johannes Kepler said. Now let's keep increasing the speed though. So increase the speed, look at what happens to the orbit, and eventually you're going to find that you get an orbit that's so fast, so the speed is so fast that the kinetic energy becomes greater than the potential energy. So then what happens is the total energy becomes a positive number instead of a negative number. And then what happens to the orbit? You'll notice that it doesn't come back. It escapes. What speed do you think you have to be going at before it escapes? The escape speed. Okay, let's go to our next slide here. So here's the discussion in detail. Rockets have both potential energy, which is a negative number, and kinetic energy, which is a positive number. And so the speed of a rocket is you add the two together. So the potential plus the kinetic makes the total energy. And the question is the total energy a positive number, or is it a negative number, or it could even be 0? So if the speed of the rocket is less than the escape speed, then the total energy turns out to be negative, gravity is winning, and it has a closed orbit, an elliptical orbit. If, on the other hand, the speed is just right so that this equals the potential energy, then when you add them together you get a 0, then it escapes. It has escape velocity. And so that orbit is going to be called a parabola. And then finally, your speed could even be greater than the escape speed, and then it still escapes, but it has a different kind of orbit called a hyperbola. So those were the different kinds of orbits that Sir Isaac Newton came up with. Now Kepler, he knew all about the elliptical kind of orbit, but he didn't know about the parabolic or the hyperbolic orbits. So you could even, so this thing here, again, summarizes what we just said about how if the speed is equal to a certain speed called the circular speed, it goes in a circle. If, on the other hand, it goes faster, that circle stretches into an ellipse, but it's still bound. It can't escape. Now, if, on the other hand, the speed is this critical escape speed, it escapes and has the parabolic orbit, and then finally you can go even faster than the escape speed, and then you go into the hyperbolic orbit. So I calculated using, there are formulas that actually can be used to calculate the escape speed and the circular speed, and I'll show those to you later. But here, for example, is the circular speed for an object in orbit around the Earth needs to be going at 7.9 kilometers per second, and then it would go in a circular orbit around the Earth. If, however, it could go at 11.2 kilometers per second, it would escape. Now look at the moon. Do you notice that the moon's circular speed is 1.7 and the escape speed is 2.4? So why is the escape speed less? Because it's got less gravity, so therefore it takes less speed in order to be able to escape the gravity of the moon. So this is one of the reasons why we want to build a moon base, is it would be easier to launch rockets from the moon than it would be from the Earth. Then Jupiter, well, look at it. Its escape speed is 59.5, much bigger than the Earth's because Jupiter is much more massive. It has more gravity. And then the Sun has an escape speed of 617.6 kilometers because it's really big. And then I did want to show you, though, there is a man-made satellite named Voyager 1 that is currently going at 17.5 kilometers per second. So has it escaped? Yeah, it has escaped the gravity of the Earth, so it's never going to return to the Earth because 17.5 is greater than 11.2. So Voyager 1 is currently on its way out of the solar system. Okay, let's stop here, and when we come back, we're going to talk about another finding that Newton made about astronomy.